So I'm going to give some very brief introduction to proof complexity, propositional proof complexity. And the main focus will be on the resolution proof systems. And some specifically proving lower bounds in this in the proof system. So like Russell, I made a list of some of the papers that I will reference. Now, okay, I'll talk about them a little more. I just want to say that the beginning of proof complexity as a subject probably should be traced to Cook. Even his famous NP-complete paper in '71, actually the title is The Complexity of Theorem Proving Procedures, and that's the focus of his paper, really, how difficult it is to prove theorems. And then he went into the formalization of propositional proof systems with many structural theorems together with his student Rachel a little later. So let me tell you what it is about. So we know that the class SAT, which is all formulas phi, so that let's say phi is a CNF formula. But this class is NP-complete. Okay, so this is NP-complete. It captures lots of the things we want to do and cannot. It's complete, meaning it captures all search problems of the type find an object that's easy to prove that it exists. That's sort of the positive or the existential side of the coin. The negative side of the coin, the complement of this language, is unsat or contradictions, which is just the same type of formulas, but there is no satisfying assignment. Okay, so all formulas that have no satisfying assignment. And this, of course, is co-NP complete. So if you are given a formula and you want to decide whether it has no satisfying assignment, well, that's exactly as hard as deciding if it has a satisfying assignment. But what you can start wondering about is, if I give you a formula like this, how do you prove to someone? Is there a short proof that it has no satisfying assignment? And that kind of question distinguishes it from this class, because here, proving that there is a satisfying assignment just entails giving the satisfying assignment. And here, it's not clear what to do, even if you have this non-deterministic power. So the question is, short and efficiently verifiable proofs. But of course, this kind of question, in its full generality, is just whether NP equals co-NP. Right? If it does, so it's the same thing as so we are not going to answer it. And the beauty of proof complexity, or what's called Cook's program, is that this kind of question, in some sense, can be approached through a sequence of steps that are much weaker than a statement like this. So we want to prove that these classes are different. But you can approach it through a sequence of steps that are maybe leading into it, but anyway are interesting in their own right. And how do you do that? Well, you simply look at a collection of proof systems. You look at which are restricted, which are not, just efficiently verifiable in the general, polynomial time Turing machine sense, but actually they have structure. And in fact, these proof systems that have structure, the structure is extremely natural and capture lots of things that anyway people are doing when they are trying to prove various things. So what do I mean when I say that the proof system has structure? Well, you're given here a CNF formula, so phi is C1, C2, C maybe M on, let's say, some Boolean variables xn, which maybe I'll call x. You are given this, and you want to prove that there is no satisfying assignment, right? So you can think of this as a set of axioms. So we will refer to them as a set of axioms. So to assume that they do have a satisfying assignment, and you want to somehow infer other, so just a collection of axioms, you want to infer from them consequences using some kind of reasoning. And you infer, so you have this, you put these axioms here. Let's call them A1, A2, AM. This will be the same as the C1, C2, etc. And then you infer from them more functions. Let's say T. You keep inferring them, so somehow each AI is either an axiom or AI is implied by some AJ1, AJ2, some constant previous one, so J1, JL is less than I. So it is implied by previous things you have already inferred. And if this inference rule is sound, and sound means just that if all of these were satisfiable, then this is satisfiable. Okay? So sound means that sound just means that if there exists an x such that a JL of x is 1 for all these previous, usually we'll just have a binary rule, but anyway, it could be more elaborate. Then this implies the same x, that this implies also that AI of x is true, right? So you are, inferring the satisfiability of new functions from old functions that you know are satisfiable by the same assignment. If you have such a sequence of, things that you infer in a sound way, and moreover, the last thing you infer is the empty function, the function which is constant 0, then you prove that there was no satisfying assignment to the original set of clauses, right? So this would satisfy the criteria of a proof system, and it's much more structured. There is no, general Turing machine which just does something crazy. All these AIs, so all these AIs are just functions. Let's say Boolean functions in this case. On X, okay? So the question is, which kind of rules should we allow? And they have to be sound, that's for sure. But in fact, there'll be some semantic structure. So these formulas will, so there'll be Boolean functions, but they will have structures. So there will be maybe polynomials, maybe linear inequalities, maybe polynomial size formulas, maybe circuits, maybe clauses, maybe constant depth circuits. So you can choose, you can take your pick of a collection, natural collections of functions. So that will distinguish the proof system. So from some class. And the sound inference rule will have some structure. So let me give some examples. It will not be too mysterious. It's not mysterious at all. In fact, you know, we are doing these kind of things all the time. We just don't call them proof systems. So first, let me note that you know, I was using clauses because CNF is NP-complete. We might as well argue about clauses, but clauses can be represented in a different way. We may have a clause that's x or y or z, and then it's a natural Boolean function. But we can equivalently, let me add something. Let's say complement here. This the same as writing, for example, a linear inequality of the type x plus 1 minus y plus z. The truth of this is the same as the truth of this linear inequality. And this is the same as the fact that a certain polynomial is 0, I guess, 1 minus x times y times 1 minus z. Right? So you can, you know, it's a polynomial, let's say, over GF2. So you can think of the axioms as a collection of polynomials that you want to prove have no common zero. You can prove so that would fit algebraic situations. You can think of them as a bunch of linear inequalities on Boolean variables, so the setting of integer programming, and you want to prove that this polytope has no integer point. Or you can think of them as just a Boolean formula, and you want to prove that there is no assignment. So this is how you can you know, think of them in different settings. Also, the inferences that you have in these different settings here, the kind of logical deduction rules that you allow, are, you know, let me just write this. Here, so we have like geometric or algebraic or Boolean views, and they are all equivalent in terms of representation of the set of axioms. In terms of inference, you can think of, in the geometric case, one, you know, I'm just giving you examples of some sound logical rules. If you have L1 of x, such linear inequality, and L2 of x, then you can infer L1 plus L2. You can add inequalities. Right? That's sound. If there was if this was satisfiable, then this is satisfiable. By the way, this is a notation that's often used. One often uses it from this set of formulas. You can derive this formula soundly. So you don't write an error, often you write. That's a kind of language here. Here, if you have some polynomial, you know, some polynomial p and q, you can derive p plus q. Or if you have a polynomial p, you can always derive p times q for any q. Right? If this is 0, then p times q must be 0. Stuff like that. So that's sound, and that's you know, structured. And here you can have, so if you have two formulas, you can certainly, and if you have f and g, you can derive f times g, for example. Or if you have a very famous one, if you have f and f implies g, then you can derive g. That's a modus ponens one, right? Stuff like that. So each one of these defines a proof system, and you can start wondering what is the power of this proof system. Namely, given a contradiction, contradiction and tautology are synonymous, having all values 0 and all values 1 is just a flip of a bit. So given a contradiction, what's the length of the shortest proof in a given system that would, would prove this contradiction? So what is the motivation for studying these kind of things? One is I said already, it's you know, sort of, you can think of it as, you know, if you strengthen this line of derivation. So you can think of it as going to, if we can prove lower bounds on stronger and stronger system, maybe we can get to this. It's hard to believe, but actually it's certainly a nice program.
So without any restrictions on the AIs or the types of inferences, is this completely general?
No, it's not completely general.
So what else could you do besides?
You can have a Turing machine that crunches the axioms and says yes. And as long as you can verify as long as there is, so you can think of an arbitrary string, as long as the polynomial time Turing machine looks at the axioms and looks at the string and, you know, says yes only on the contradictions and no otherwise, then it's a proof system.
I mean, what reasonable operation could it do besides this? Can you think
it can take the sign function of the binary representation of the clauses and then, you know, raise it to the 7th power. I don't know. And take the least significant bit, yeah. So that's why we don't understand. That's why we don't understand. Okay, so that's one motivation. Another motivation is search algorithms. So last week, Russell talked about basically about the complexity of search procedures for, you know, various things like solving satisfiability and so on. Many of them, you know, are branching bound techniques, various techniques that look for satisfying assignments or for cliques or for whatever you want. Doesn't matter that they are exponential time. Sometimes they look and sometimes they don't find what they want. Sometimes in particular branches they don't find what they want. In these cases, they are, you know, they have to say, well, this leads nowhere. I can backtrack or I should backtrack. This is a, so the problem of, you know, showing that there is no solution to some problem or some restriction problem is part of most search procedures. Moreover, most search procedures are using various, you know, types of reasoning. For example, you know, this type of reasoning is the geometric reasoning, is the reasoning behind the cutting plane, you know, the Gromari cuts and, you know, standard ways of trying to solve integer programming. And this kind of reasoning is the natural algebraic one behind the Null-Challenge proof system or the Grobner proof system. That people are using to solve polynomial equations. And here, various, you know, Frege proof systems are natural in the Boolean setting. So if you have a lower bound on any such, you know, on any such proof system for a concrete tautology, you also have, you know, you have definitely have lower bound on algorithms that use this reasoning that are searching for whatever satisfying assignment. So this gives lower bounds on search algorithms of certain forms. And they are very strong because what you are proving, if you have a lower bound, you are proving a lower bound on a non-deterministic algorithm. Even non-deterministic algorithm cannot do what this algorithm, this deterministic algorithm is trying to do. The third one, we sort of developed independently. Well, I guess Cook, of course, knew about it. Is the papers I wrote there, at the top, the Davis-Putnam and the DLL paper. So this is automated theorem proving. For some of these systems, proof systems, you might hope that if they are simple enough, maybe the existence of a short proof will actually allow to search for the proof and find it, and then, you know, have a proof of a theorem that's encoded in this in this propositional way. And I will not talk much about automatizability, but definitely many of the automated proof systems are based on, Russell mentioned DPLL, which is sort of the combination of the class of combinations of these procedures. And that's definitely a motivation, understanding the power of different proof systems and the trade-off between their power and their automatizability. Obviously, the more powerful they are, the harder it is to expect that if you have a short proof in the system, then you have a fast algorithm in the system. And the last one is somewhat remote, but maybe I'll get time to talk a little bit more at the end, is restricted independence result. We don't know whether P is different than NP. Some people believe, most people believe it's different. Some people speculate that they are equal. But there is a third possibility, of course, that they are independent. So this question is independent, let's say, of set theory. It turns out that lower bound, in the beginning of proof complexity, I think that people in logic and other people were not really interested for the usual reason that they are not interested in finite things. What does it teach us? What can this teach us about real proving of the Riemann hypothesis? As it turns out, there are connections, and propositional lower bounds on propositional proof systems can be interpreted in certain settings, can be interpreted as restricted independence results from very tiny fragments, small fragments of piano arithmetic. So you can interpret some lower bounds here, concrete lower bounds for propositional tautologies, as restricted independent results from piano arithmetic, from fragments of piano arithmetic. And Razborov is one of the people who pursued this direction. So maybe I'll mention, what some lower bounds, even on resolution, say about P versus NP. Okay, questions so far? It was, of course, longer than I planned this.
So what's the intuition for the fourth part, this restricted independence?
Well, since I said that's not the focus of the talk, so I'll talk at the end, or you can ask me at the end if I don't get to it. It's very interesting. But let me say in one line, well, if you know, for example, what the connection between oracle separations and oracle separations in the polynomial hierarchy and AC0 lower bounds, original motivation of Fersach-Sipser, then it's a similar translation. But okay, so we are down to back to resolution, and again we had phi C1, well, maybe just a collection of axioms. And here the simplest, so that's what Davis and Putnam suggested, that's essentially the simplest proof system you can have that's not really trivial, for which proving lower bounds is not completely obvious. It's not obvious at all, in fact. That's the whole point of the talk, to show you some techniques for proving lower bounds. And it's the following. It's just how can you infer? So first of all, the class of formulas in the proof will be just clauses. So we'll have C1, C2, Cm, and then we'll have Cm plus 1, Ct. And they are all the Ci's will be clauses. So this proof system operates with clauses. All the formulas it ever generates are clauses. So that's the simplest possible. And how can you infer a clause from other clauses? It's almost the only way you can do it in a sound way, and that's the restriction of modus ponens to clauses. It says the following: if you have a clause which contains a variable x, so I'm just explicitly writing the variable here, and you have another clause which contains the complement of this variable, then certainly it's sound to infer this. Okay, throw away the variable. It must be that, right, one of them is true by itself. Okay, so that's I can write this down. Okay, so that's this is it. So I give you a tautology.
We allow something like adding a variable.
You can allow what's weakening. You can allow adding a variable. I won't even write it, yeah, because it wouldn't affect any of the proofs. Yes, it makes sense to allow adding a variable to weaken your clause. So can we prove any lower bounds on any tautology? So that's a big question, and let me start writing just examples of some tautologies that are interesting in the, anyway, they're interesting, and it's interesting to study them for any of the proof systems we discuss and we didn't discuss. And so just also it will be, maybe for those who haven't seen, you'll see some tautologies. So let me use this side of the board to write tautologies. So here's the Pigeonhole Principle. That's by far the most famous one, the Pigeonhole Principle. The M and N. M and N are, M is the number of pigeons. So M will be larger than N. M is the number of pigeons, and N is the number of holes. How do you represent the Pigeonhole Principle propositionally? You want to say that there is no injective function from M to N. So one way to represent it propositionally is you have a variable xij that supposedly denotes whether pigeon I goes to hole j. Okay? And so that's what it's supposed to denote. Now you want to say that it cannot be one-to-one. So you have to impose this. So I'm going to write to you the clauses which define this contradiction. What are the clauses? So there are the pigeon clauses. So somehow the clause for pigeon I is just says xi1 or xi2 xin. This says that every pigeon has to choose a hole, right? So this has to be true. And the other thing is that no two pigeons occupies a hole. So the hole j clause is so this is for every I in M. And for every j in N, for every hole in N, for every two pigeons, I1, what you want is that either you don't want two pigeons in the same hole, so x I1j or x I2j. Okay? So they cannot go in the same hole. And you have this for. So it's a bunch of clauses. It has no satisfying assignment. It's polynomial size in M and N. How, what's the shortest proof for this? That's one example. Here's another example. It's citing tautologies. There's some graph G. Okay, ask me questions if anything is unclear. So what's the citing tautologies of a graph G? Well, let me write here. Let me write the equations in not as clauses, but we'll soon write them as clauses. So you have this graph. This, by the way, so this talk was partly motivated by people asking questions about Chris's lecture in December about time-space trade-off for resolution. Is a paper with Russell and Paul Beam. And the result, I'm not going to talk here about space trade-offs. I'm just going to talk about size, lower bounds. But anyway, the type of tautology for which they prove this size space trade-offs was citing tautologies. Citing also one of the originators of the study of the resolution proof systems and its complexity in the 60s in Russia suggested this. So here you have a graph. And think that for every edge, you have a variable, that's xe. So for every edge, you have a Boolean variable. And you think of the graph as just describing a system of linear equations. And the system of linear equations is the following. So there is some implicit Boolean vector here, b, which is not really necessary, but let me write it. So for every vertex, you write an equation that the sum of xe, where v is, all edges touching a vertex, is bv. Okay? And this for every p and v. So it's a system of linear equations. What?
Reals or GF2?
No, it's all Boolean. Everything is Boolean. So this is GF2. So all Boolean. Okay, so it's a system of linear equations. It's very easy to see that we want a contradiction. We want something that's not satisfiable. So if we make sure that the sum of BV is 1, right, the sum of these charges is odd, then this has no satisfying assignment. Because if you add up the left-hand side, you get 0, and with the right-hand side, you get 1. Okay, so it's a contradiction. It's not quite a set of clauses, but if the degree of the graph is small, if degree of G is at most D, some constant, which it will be in all examples, then it's very easy to encode the, so how do you encode the, just how do you encode x, y, let's say, y bar. How do you encode this in a set of clauses? This is the same as, I guess, some n clauses. So they should not all be 0. So, x either this or y or z bar. It can't be that 2 of them are 1s. So you can, it's going to be that 2 of them are 1s. So either this is...
So they cannot be all 0. That means that x or y bar or z.
Yeah. So this is certainly true, right? They cannot be all 0s. I mean, in order for this equation to be satisfied, they cannot be all 0s, all these 3 literals.
Oh, you just have it complemented.
Yeah. At least one of them is 1, right?
Yeah, but now do you say that it's one of them is 0?
Oh, maybe I should, yeah. Well, okay, there'll be 4 clauses here which you can complete, and right? So this is equivalent to a bunch of 4 clauses, and so on. So you can encode it, and if you have the degree is d, you multiply, d is constant, then the description of the system is still, the factor of 2 to the d by constant factor larger as a CNF. So these are the citing tautologies. So that's another important family of tautologies. Here's a maybe even more basic set of or contradictions. Here's a more basic set of contradictions, which is random. It's just, C1, C2, Cm are random, let's say 3 clauses. You can do k clauses, random k-CNF or random 3-CNF. We know that if we take enough clauses, if we take, I don't know, 10 or 20 n random clauses, then with a very high probability that will be unsatisfiable. So what's the length of proving it? It's a very basic question. Let me note, by the way, that here such a family may be satisfiable. We are proving lower bound on the shortest proof that there is a contradiction. If there's no contradiction, certainly there's no short proof of it. Okay, so we are interested only in what happens if it's a contradiction. Similarly here, if B, this vector sums up to 0, then it's not a contradiction. Anyway, so what about this? Okay, let me mention two more. A very important point to say about this example. So these two are very explicit examples of contradiction. This is random. When I want to put some contrast to Boolean complexity, but to circuit complexity. In circuit complexity, we only search for explicit lower bounds. Random lower bounds we have, there's just a counting argument. Want to prove that circuits are big, most functions require big circuits because there are many more functions than circuits, than small circuits. This absolutely falls in the proof complexity world. The number of tautologies is just polynomial. Right? The difference between tautologies and functions is functions can be 0, 1 on every input. This is 0 on every input. So they're just polynomially, they're just exponentially as opposed to double exponentially many short tautologies. So we cannot use a counting argument. Therefore, it's interesting to prove complexity lower bounds, even for random contradictions. We have no tools for doing it for complex proof systems.
In fact, here it's harder for random. I mean, in some sense, harder for random. Because the first two are trivially in co-entry, but I don't know if this random is in.
I don't know if it's harder. It's just it says well. It's not clear that it's harder. It's not clear that it's harder. It's
You have your jacket attached.
yeah, that's a good point. Somehow, hopefully this will work somehow. It's okay. Okay, so let me mention two more. Then we have to, at some point, go to lower bounds. These two I will not write down explicitly as clauses, but one of them we'll do later more explicitly. So this is cliques versus independent set. So the tautology here is that, or the contradiction here, whatever way you want to think about it, and you will encode it propositionally later, is that no graph has a k-clique and a k-1 coloring. I wanted to write coloring there, k-clique versus coloring. Okay, that's another tautology which you can encode propositionally, and we'll look at this. And finally,
You mean here by no graph, you mean actually explicit graph, right? That's big.
I'll tell you how to encode it. Yeah. But you believe the statement that no graph. Yeah. So that's what it. So just like in the sense that the Pigeonhole Principle encodes that there's no one-to-one function from a big set to a small set. Yeah. And the last one is the one I sort of alluded to when I talked about this independent result, independence results. And this is a sort of a Rasborov tautology, saying that so the tautology encodes the fact that a given, so like here, no graph, so a given Boolean function has no small circuit. Okay, that's another tautology. Okay, so these are the tautologies I want to talk about today. We'll see if we get to this. Here's what we know. So now let's put some results here. So this paper of Haken in '85 says that PHP. So maybe I should let me do some. Let me denote S of phi is the smallest resolution proof of phi, and I'll also talk about smallest tree-like proof. The length of a proof is T, the number of clauses you generate. If you think about it, this, because we are inferring later ones from previous ones, we can draw it as, in a circuit structure, right? We can start from the axioms here, and, maybe we resolve here and we get Cn plus 1, and maybe we do some other resolution and so on. And eventually we get to the empty clause, right? So this has a general directed acyclic graph structure. When it is a DAG, then we talk about S. When it's actually, this DAG is a tree, there is no, right? And when it's a tree, we talk about S sub T. So this is like the difference between circuits and formulas in the Boolean world. And also here, it's good to distinguish them because there are stronger results for the tree-like resolution.
If it's a tree, then the same axiom may occur
many times, yeah. So the leaves are the axioms, and every node, internal node, is a resolution step. Yes. Just like in formulas, the same variable may occur many times. Exactly. Okay, so I'll use this. Okay, so Haken, that was a real breakthrough paper, the first exponential lower bounds, PHP n plus 1 n, so n plus 1 pigeons cannot fit into n holes, prove this lower bound. And a little afterwards, Schwatal and Semeredi, I have here, prove the same for random, let's say, 10n and 3NFs. In fact, they proved it for general KCNFs. It should be clear what I mean here. I say that for almost every collection of 10 clauses over n variables, 3 clauses over n variables, the length of the proof is at least exponential in n. Since very few of them are actually satisfiable, it really says something about most unsatisfiable. So it's not a trivial statement, right? Because most of them are unsatisfiable. You can put 100 here. Okay, so with high probability. And I think it was earlier, but I think the journal version of Urquhart's paper is 95, that the size of the Zeitin tautologies on expanders, constant degree expanders, okay? So if you, these graph tautologies, these linear systems are, okay, and then I think, I'm not sure about the date of this paper, maybe Russell remembers, sometime mid-90s, there is the interpolation papers. It's around the mid-90s. So, I don't know, mid-90s. Both Krajcek and Razborov proved that this clique well, it depends. If we do k cliques and k independent sets, then this should be something like n to square root k. Certainly to test k cliques or k color, sorry, coloring. Testing k cliques can be done, and in fact, even deterministically in n to the k times. So proving a sort of more or less tight lower bounds here. And why did I separate them? Because I wanted to prove, to talk about, and maybe I should mention the last one. So here in the late 90s, in around 2000, Raz and Razborov, it's not the same people. Started with this amazing breakthrough of one Raz, and then some simplifications of Razborov proved lower bounds, exponential lower bounds for NP. Exponential lower bounds here. The reason I separated them is that there are different proof techniques. And let me start from the end. This I'm not going to talk about at all. This is the interpolation method. This is an amazing tour de force. It's interpolation method. Let me back up. Let me say something about this. Let me say that to prove this, what you really prove is a lower bound on the size of PHP, 2 to the n. And you can put infinity n here. In fact, I think the bound is 2 to the n to the third. So you prove a lower bound. Well, in general, the more clauses, the more axioms you have, the easier it is to, prove something. You don't have to use them all. So let's say you want to prove that, 2 to the n pigeons don't fit in. This turns out to be much harder than proving that n plus 1 pigeons cannot do. And not only is it harder, 2 to the n is not the right lower bound if you have more pigeons. Tony Pitassi observed long ago that S of PHP 2 to the n, even less, n, is at most 2 to the root n, at most. There are short resolution proofs, shorter than you might imagine, when you have really lots of pigeons. So proving this lower bound is not just, it's harder, but it's a different nature. Okay, but let me not talk about this. So this is by the interpolation method, which I want to explain to you, and that ties very, very nicely proof complexity into circuit complexity. So this is really based on circuit lower bounds. And this proof method, well, for anyone who got to look at these 3 different papers, the one thing you would know for sure is that they are extremely complicated and long and involve lots of arguments and messy arguments and complicated combinatorial lemmas, and it's very hard to understand them, even though there are clear ideas there. Then Eli Ben Sasson came and asked me to do a PhD with me, which was great because the first thing I let him do is read and explain these papers to me. So, and then we tried to make sense of them, and we developed this, what we call this width method. Width method, which simplifies all of them to the extent that I'll try to do it in half an hour to you. This width method is based on an idea that appeared in these 2 previous papers, mainly this one, Clegg, Edmonds, Impagliazzo, and Bimkar, Pitassi, Sachs. This has to do with a completely different, the Grosvenor proof system. This has to do with automatizability, but there is an idea there that enables to really clean up all these, to really elucidate the ideas in them and get rid of a lot of mess that happens there. But so I'll explain it in a second, but let me tell you something about the mess that happens here. Okay, because this kind of mess seems to be essential to stronger proof systems. We don't know how to elegantly get rid of it for stronger proof systems, like Frege proof systems or restricted Frege proof systems. So what is the idea behind Haken's method, which the others then use? The idea is the following. If you have, assume you have a short proof for something, for any tautology. You have a short proof, sub-exponential proof. Then, well, it's just a bunch of clauses, right? Suppose you hit the proof with a random restriction. Okay. We know that hitting constant depth circuits with random restrictions kills them, almost kills them. But certainly hitting clauses, I mean, if you have a long clause, a clause with a linear number of variables in it, then you kill it with exponentially high probability. Becomes a constant, right? So that's great, because if you have a short proof, just sub-exponential number of clauses, in particular, you have sub-exponential number of short clauses. So you'll kill them all. So there'll be no long clauses remaining. And then, if you are really lucky, and that's really a complicated point, but if you are really lucky, you didn't kill your tautology. Sometimes you'll randomly restrict a set of clauses, and then a contradiction can be found within 10 clauses as possible. So that you have to be careful, and that's really complicated. But the idea is hit your proof with an appropriate random restriction, hopefully not killing the tautology. And then what remains has only short clauses, sublinear, right? You killed all the linear ones, so you have narrow clauses, right? Prove that there is no such proof. Prove that, every proof of the remaining tautology, hopefully Pigeonhole will remain Pigeonhole after restriction and so on, cannot have short proofs, short clauses. There must be some long clause in the proof. In these arguments,
when you say kill tautology, when you said before, you mean something that might have proof consisting of shorts.
Yeah. So the restricted tautology, which hopefully will be of the same type of the original one, cannot have only short clauses. As it turns out, and this is the Witz method, which I'm going to explain next, you don't need the random restriction. You don't really need for resolution. You don't need the random restriction at all. There is no reason. And this takes a big volume of these papers. You don't need it at all. It's sufficient to show that the original tautology does not have only short clauses in it. It must have some long clauses. This alone will imply a lower bound on side. So that's the Witz method. So that's where it really simplifies these papers. But I do want to say that, we'll take a break now, I guess. I do want to say that the random restriction method, this doing what I described is redundant here, is absolutely essential for stronger proof systems. And this not only led to, progress of this idea, didn't only lead to improving lower bounds for stronger proof systems, it also led to an improved understanding of the random restriction method in itself. So in order to start doing it, Razborov developed a very different proof of the Hastad switching lemma. I don't know, it's now commonly taught, in fact, more than the original proof. Beautiful proof which had the proof theoretic advantages. And also, it's very easy to tailor this particular idea when you are doing random restrictions for stronger proof systems. And Paul Beam wrote a survey about it, and Russell used it in at least 10 papers and so on. So that's a very important thing, which we are not going to see because in what I'll show you, there is no random restriction. Okay, so we'll take 5-minute break. Questions before that? Okay, so I'm going to explain this with methods. And the take-home message from the with method and from this set of tautologies is expanding tautologies are hard. So this expanding, we'll have to make sense of this. Tautologies are hard. So there's a common explanation to all these lower bounds. And here, it's more like disjoint, NP complete pairs are hard. Hard, I mean hard for resolution. Okay? So now because, like with Russell, I see that I have much less time than I planned, the sketches will be more sketchy. But I think all the ideas are really simple, and you can figure them out yourselves, and also read about them if you want to cheat. So what's the width method? Actually, our paper is called Short Proofs Are Narrow. And you don't need random restrictions for this. If you have a short proof, then it's narrow. Okay, so why is it true? So so we have these two parameters, size and tree size, and width. Width is just the number of clauses of the widest clause in the proof, in a resolution proof, okay? And the two theorems here is that is at most log. Width is at most logarithmic in the size, in the tree size. So if you have a tree-like proof, then it's logarithmic. And the width is at most, so it's also somehow related to size, but in a weaker way. So it's at most the square root of n log. Okay. But notice that in both cases, so you can figure out the reverse inequalities, but in both cases, if you prove that both the tree size and the size itself, so that's right? I mean, even this weaker relationship is still true. So we will prove linear with lower bounds, and then this will imply both. Let me note that these results have another corollary that I will not write down, that in some sense was known, but sort of proves it very simply about the automatizability of the resolution proof system, right? So it says that if you have any proof of some size, tree-like or untree-like, then there is another proof which has small width. But proofs of small widths are easy to find. You just generate all clauses you can, never going above this limit, right? So in n to the width, you can, find such a proof. So this has implications to finding proofs once you know they exist. But I will not write it down.
Are we defining width as the minimum width over all proofs?
Over all proofs, yeah, not necessarily finite time. Right. So let me explain the idea for the tree-like, and then I'll mention something about the idea for size, but it's the same. So here's the idea. So suppose you have a tree-like resolution proof. So you have, here's the empty clause. It's generated by a resolution rule, so there must be some variable xi and variable xi bar here, which were generated by two parts of the proof from this whatever clauses. Right? That must be the case. And if the proof, if it's of size s, then at least one side is at most s over 2, right? Now, we want to find a narrow proof for the same thing. So let's do it the following way. So I claim that width of this tautology, think of restricting xi to 0, right? And restricting it in all the things here, okay? Then we have by induction, so we will do induction on, so this proof is by induction on both n and s. So let's assume we are already on with n variables of size n, size s, and we know it for all smaller sizes and number of variables. So here we have a proof of a restricted tautology. We just set xi to 0. So when we restrict it in all these clauses, so we have some collection of subclauses from which we derive the empty clause. The proof is of size s over 2. So we can do this proof in log s minus 1. Right? So I'm not done yet. So we have log, so log s, right? Log s over 2. So we can do this in small width, just this left side. We can do a small width by induction. Now in this proof, add xi to every clause, okay? Add xi to every clause. So we start now back with the original clauses, we generate xi, but we increase the width plus 1 by 1, right? So we have generated another, so this left side, so let's call it L and R. So we have another version of L which is very narrow, which generates, it's an alternative to this, which generates xi, right? Use it, so generate it, and every clause here which has xi bar in it, so there are various clauses, every clause which has xi bar in it, you can resolve before you start this part. Before you start this part, you can resolve with this xi to eliminate it. So you are going to plug this narrow thing down here to eliminate all the occurrences of xi bar. Xi it will never be used to generate xi bar, so you can forget about it. So you remove, basically, practically removed xi, the variable xi, from this part of the proof, and because of this, you already generate the contradiction here. You just eliminated in advance xi bar, so you'll generate it already here. Now this is, again, a tree-like resolution proof with one less variable. We know that we can do it in at most log the size. So it's so the new width logs the width. So it's the maximum of this and log s. That's from the left induction, that's from the right induction, but both of them are log s.
Why is the size s? I mean, you appended those.
No, I didn't append. That's how the new proof will look like. I'm using the fact that without the variable xi here, in this smaller contradiction, this is a size s proof, it has a proof of small width. Now the total proof will just do this first, and yeah, so it's a reverse direction. Okay, so that's how you prove that if you had a short proof, short tree-like proof, you have a short, you have a small width proof. Not tree-like. You can make it tree-like. It doesn't matter. Width doesn't care about the structure. It may be much longer than the original proof also. It's not tree-like as this. But we don't care. We are just, it's a reduction, right? What this theorem is saying is that to prove lower bounds on size or tree size, tree-like size, all you need is to prove lower bounds on width in any proof. And that's what we'll do. Okay, this is for the tree case. The case of general formulas, general proofs. So this is one. I'll say it in words. Somehow you want to get a formula, get a proof like here of a smaller size. Right? Here it's given to you. The tree-like structure tells you where to look, tells you what is this proof and what does it prove and so on. But the same idea applies in a general proof. You have this very long general proof, and first of all you say, well, I don't care about the short clauses. Those that are shorter than this, let me ignore them for a second. Okay, let's call this W0, this number. So let us mark only the guys that are at least W0 in length. Okay? Now, and this is my real size parameter. I don't care about this, the short ones, because short I like. So, but those that are long, there must be a literal that appears in many of them, right? At least in a fraction 1 over 2n of them. In a fraction W0, right? So there exists some I, so the xi occurs in 1 minus W 2n of them, of the long ones, right? And then you do the same.
In
W over 2n, W0. Yeah.
1 minus? No, 1 minus.
Oh, sorry, yeah. Right. Yeah, or my 1 minus. Yeah, once you remove. And then you do the same trick. You apply induction on the rest. So you set it to 1, just like, or you set it to be true, just like here. You have a smaller thing that derives a contradiction, something smaller by 1 minus W0 over 2n. And let me not do it. You do it in the same way as in this picture. This is how you find the variable you should set and then eliminate in the second part. And it gives this result. It's very simple. Okay, so now how do you prove with lower bounds? So now we want to say that certain tautology is every resolution proof of some tautology is wide. So what's the idea? The idea is the following: we have this proof, and somehow we are concluding the empty clause. You see one. Somewhere we have C and D, and we resolve them to give, I don't know, E. We want to prove that somewhere one of these clauses is wide, is linear, has a linear number of variables. This comes in 2 steps, okay? The first step is building some very natural formal complexity measure on resolution proofs. Okay, what's the formal complexity measure on resolution proofs? And I'm telling you one, and then you have to play with it a little bit. It's very flexible to suit it any one of these tautologies, the ones we are proving lower bounds. But I'll tell you a basic one. Here's a basic one. Mu is a complexity measure. It's the smallest, the size or the number of some minimal number of axioms implying C. So right, it's all sound rules. Everything that we got is implied by some subsets, certainly by all of them, but what's the smallest that's really needed? And the nice thing is that this measure, there's several obvious things. So let me just write axiom is 1, right? Every axiom implies itself. mu of E is at most mu of C plus mu of T. Right? To get E, we just, right? It's subadditive. And this thing you have to arrange, mu of the empty clause is linear. And, you know, if you pick out tautologies, you pick them so that, you know, you throw away the one. Yeah.
It's not true that you can delete.
Yeah, you can delete the axioms. But anyway, that's a very natural thing. Like,
So this will not be true for the pigeonhole principle, except for an n+1.
it will be true. Okay, so let me say something that I should have said earlier about the pigeonhole principle. We'll come back to it in a second. These lower bounds are sort of not interesting for if you have wide axioms in the wide axioms, right? I mean, this is interesting if let's say you start with a 3CNF or a constant size axioms. And this will be the case in essentially all of them. I'll tell you later how to arrange it for the pigeonhole principle. In general, you can always do it using Cook's reduction by adding variables and making everything a 3CNF. It's not always nice to do, but that's one way to do it. But it will be true also for the pigeonhole principle. This thing. Yeah. Basically, if you have one pigeon missing, then it's not true. Now, what you're saying is that all these guys, you know, they're in the pigeonhole principle.
No, I mean the 2 to the n pigeonhole principle.
No, sorry. So the weak pigeonhole principle, that's right. It will not be true. Yes, thank you. That's a very good point. I thought you
It'll
meant.
still be omega n.
Yeah.
You need at least n different.
You need at least n pigeons, right? It's a little. I mean, this thing changes a little bit for the pigeonhole principle, or in fact for every one of them. But let's just do this argument, okay? Okay, because this is, you know, very easy to arrange, and you have this. There must be for every k you pick, and we'll pick it to be some. We will pick it to be some constant times n. In most of these examples. But you can pick whatever you want for other purposes sometimes. Any k you pick, there exists E in the proof, in any proof. There must be, so whose measure is between k over 2 and k. Right? Because you can't more than double. You're going between 1 and, right? So there has to be a clause that has, you know, measure about k, let's say linear measure. Now, what does this measure have to do with width? We would like to argue now that this clause is y. There is no connection a priori. However, there is a connection in the following situation, which is exactly where expansion comes in. Okay, assume, so expansion of this set of clauses. So when do we say that it's expanding? Let's say it's expanding at k. It's expanding at k. If for every, so let me denote the boundary of a set of clauses, d1, d2. Okay. Is a subset of the variable set, is all variables that occur, variables in exactly one of these clauses. So look, this is the boundary, right? So you have a set of, it's forget the literals now, it's just a set system. And look at all those elements that occur in exactly one of them. I claim that if this set, d1 up to dk, they imply whatever it is, c, right? Then the length of c is at least the length also boundary. Is the length is at least the size of the boundary. Right? Why? Because resolution just eliminates variables when you can resolve on it. If it occurs one, you never resolve on it. So this is a natural definition of expansion. The boundary of a set system, of a hypergraph, is large, right? That's expansion. If every set of size k is expanding, then, so expanding will be, let's say that it's at least a constant times the number of members here, then you have a lower bound on the width, and then you are done. And now let me just hand wave my way into the expansion, the expansion, and therefore the width in these three examples. Okay, is it clear what happens here? So this part just shows that there's something of high measure. High measure means that the number of clauses implying it is of some size that we want. It's not too small and not too large. Yes?
So when you say D1 up to dk, you mean it's doing iterated resolution?
No. Just these are axioms. I mean, this is general. So if some set of clauses logically implies, just forget resolution.
But don't you want that all of those are needed to?
You take the minimal. This measure was a minimal. Yeah, so all of them are needed. Yeah. Take the minimal. So it's a minimal set that implies it. If it has a certain number, then, I didn't write here minimal. I mean minimal, yeah. Thanks. Then it must be at least as big as a boundary. Good, so we just want to prove that in these situations we have, expanding tautologies. Our contradictions are expanding. Okay, so let's start from the easiest one.
Can you change 1 into odd?
Can I change?
An odd number of di should.
No, not in an obvious way, no. No, there are other situations. This odd thing may come up, but not here, no. Okay. Okay, so the easiest one is really the site in tautologies, and I think that was, in some sense, his original intention. Only at the time he was doing it, there were no expanders, and he didn't know about expanders, and so he used cliques. But we'll do it with expanders because we have them. What? He used grids, but there was another thing. There was another paper which used cliques. You can get something from cliques. Yeah, he used grids. That's right, thanks. Like you do. Yeah. Okay, so let's look at the site in tautologies. So let's try to understand. We have there we replaced each linear equation by 4 clauses. But now think of changing your mu to say not which subset of clauses implies a clause, but which linear equations imply a clause. So I give you for free all 4 if you touch any one of them. Okay, so which linear? Okay. So we have this measure. So we have a k subset, let's say n over 10 of the parity equations implying some clause. What is the boundary? What is the boundary of this type of equations? Equations are on edges. So these are edges that, so here is a graph. Here is a, let's say we have here a set of, vertices, S. This is V. And this is roughly of size k, between k and k over 2. When is a variable is an edge, occur in exactly one of them. Occur is exactly one of them if it crosses this cut, right? So in an expander, we know that the linear size sets have linear size boundary, and we are done. That's it.
So what is S here?
S is a set of, so S is a set of axioms. So let's say that, the axiom, you write the linear equation of V for V in S, this collection implied some clause C. That's it. So the boundary, this is the boundary. So that's it. We are done. Expander by definition does it.
Otherwise, if you have the way that you find it, when you implement clauses, you have several clauses of the same set of variables.
That's right.
So you could have that each one of those appears twice, and you have no variables that appears just in one clause.
That's right. So what I said, let me forget about the clauses and give you the linear equation itself. And this comes to what I talked about as the flexibility of this measure mu. You don't define it as a number of clauses implying a clause. In this case, you'll take it the number of linear. Yeah, that's why you change so in all of them, you make some small change. Okay, so that's it. I don't need to write anything. That immediately implies. Let me say something about the random one. Okay, so the random one, I mean, I hardly have to say anything because the same picture. So forget literals now. You have a bunch of, it's a hypergraph, right? I mean, what is a random 3 CNF? It's a bunch of triples. Forget now the names. And with a linear number of triples on n variables. Well, I mean, it's a calculation. You can all do it by yourself to see that if I give you just, again, a set of edges, n over 10 edges in a randomly chosen 3 uniform hypergraph, there'll be a constant times n guys that are, will look like this. It's a calculation. That's it. So a random hypergraph is expanding. Okay, what about the pigeonhole principle? Well, first there are the wide clauses. But actually, so one observation we made in the paper that's in some sense nicer than the reducing the width into 3 CNF by adding variables. Suppose that I tell you already about many of these variables that they are zeros. So I just leave here, just xi2 or xi3 or xi(m). In every one, I pick just 3 locations to live alive. I fix all the others to 0. And I do it in such a way that that's an expander. I can do it, right? So first of all, I reduce the width to 3. B, expansion is the same expansion as before. Right?
What's the difference between this and random restriction? I mean, you modify the...
First of all, it's not random. You don't need to do it random. I do it in a way that the ones I leave alive, I reduce the number of variables from quadratic to linear. I arrange the pattern in a way that as a bipartite graph, it's an expander. And then you can check that the notion of boundary corresponds exactly to the expansion of this graph.
You give
So,
only 3 addresses to each.
yeah, every pigeon. Of course, it's a harder problem. Should be easier to prove. Exactly. You already know that many of the variables are 0. So that proves it. It's exactly, yeah.
Another difference is that you never set a variable to 1.
Yeah, you don't want. One of the problems with the pigeonhole principle is that random restriction of the usual type will kill the. Yeah, will give you a contradiction without working at all. Yeah. So you have most in all these proofs for stronger proof systems, the random restrictions you use for resolution are partial matchings. You pick where, I don't know, a constant fraction of the pigeon will go. It's a partial matching, and you set all the other possibilities to 0. And then it's much harder to prove various things about it. Yeah, because it's not a balance. But anyway, let's not go there.
Does 2 variables each suffice? Or do you need
No, you need expansion. 2 variables will not be an expander. Will be, yeah, that's easy to prove. Yeah.
but this method would not work. But does it?
No.
As a short proof?
Yeah.
Okay.
For 2 variables, it's like horn clauses, or it's like 2 CNF. Yeah, it's not. Okay. So that's the end of this proof. So just you prove with lower bounds, and from which you prove, you infer size lower bounds immediately. Let me mention that this kind of idea is used in, so proving with lower bound is interesting in itself for some proof systems. What we didn't say we proved, but we did prove, is a lower bound on the following proof system for linear equations. So here you start with a bunch of linear equations, which are contradictory, and you want to prove this contradiction. Just in linear algebra, it's very simple to describe a proof system that does it. You know, you're allowed to add equations till you get 1 equals 0. Okay? That's a proof system. It certainly proves it's complete and sound. I didn't mention it about resolution. It's also complete and sound. It's complete and sound for linear equations. And you can ask yourself, well, of course, this proof system has a linear size proof. You add the equations, you get 0 equal 1. So in terms of size, it's not interesting. But in terms of width, it is interesting. And what we just proved for expanding graph is that this linear proof system requires large width, linear width. So who cares? Well, it turns out that Russell and Eli Ben-Sasson have a beautiful paper in which they show that this kind of, almost trivial observation, you can lift it to the Grobner basis proof system for proving polynomial, for proving the unsatisfiability of a bunch of polynomial equations. And you can get from this degree lower bounds on the degree of polynomials occurring in any proof in this Grobner proof system, which I didn't define for the same citing tautologies over, let's say in this case would be, I guess, characteristics different than 2. But anyway, you can use width in order to argue about degree, which is a parameter of choice in this polynomial Grobner basis proof system. Okay, so enough about width. Let me tell you now about interpolation. Questions about width? Clear? Yeah. Okay. So suppose I tell you that my phi, let me pick other sets of variables, y and z. So y and z are some 2 sets of variables. Maybe I call them sets of variables. Suppose that I tell you that it's actually composed of y. Suppose this is a contradiction. What can you tell me? There are disjoint sets of variables. So, right? So if there are disjoint sets of variables, well, and this is a contradiction, it must be that either this is a contradiction or that's a contradiction by itself, right? They don't talk to each other. So it must be that, so that's a trivial observation. So let's extend it a little bit and look at other type of contradictions which have 3 sets of variables. Again, x is also disjoint from them. Three sets of variables. What can you tell me about in this case? In this case, what we infer from here is that for every choice of values for the x's, either the left or the right must be a contradiction. So this suggests a Boolean function, or a relation, but relation which is so this, if alpha is identity, so if this is a contradiction, here if beta, if x is a contradiction, and star if both So,
Probably better to say 1 if beta of x z is not a contradiction.
yeah, then yeah,
Zero.
yeah, that's right. Let's do it like this. Right, so it's not always defining this value. Sometimes it can take both 0 and 1. But think of it just for the purpose of continuation as a Boolean function. Right? So this is called the interpolant. The interpolant of this formula. And this interpolation method, or the interpolation idea, the existence of an interpolant in the propositional case is trivial. I mean, we just said it, and it's obvious that it's true. It comes from first-order logic. In first-order logic, the existence of an interpolant, which is in self first order, is not trivial. That's the Craig interpolation theorem. And then Krajicek and independently Razborov had over there had the idea of using this into reducing proof complexity lower bound into circuit complexity lower bound. And the idea, which can apply to any proof system if you are lucky, and definitely applies to resolution because there we are lucky, is that if we can show, so the hope is like this. Assume we can prove that this function is hard in a normal computational complexity sense. Maybe we can infer from it, and this is not a function, it's a collection of functions, so you have to prove that any one of these functions, this relation, is hard in a Boolean complexity sense. The hope is that this will imply that any proof of this tautology is large. Now, why should this happen? So let's look. These are particular type of tautologies, and let's see why it happens for resolution. Okay? So it's clear, but the hope is that F has high complexity. Will imply that phi of proof. And this implication depends on the proof system, and it would work if, so this will happen if the proof system, in this case, resolution, has efficient interpolation. So what should an efficient interpolation mean? If you have a short proof of this tautology in your system, then you have a short circuit of your interpolant. That's what efficient interpolation means.
Why is it called interpolant?
What?
Why is it called interpolant? What's intuition?
It's called interpolant because if you make a different picture of if you write the, it will not explain it to you really, but Craig's interpolation says in first order logic, if you have, what did I call them? Alpha xy implies beta, logically implies beta of xz, then there exists an f, just the f that we talked about, such that in fact alpha of xy implies f of x, which implies, and that's if you want to call this interpolation, then it's the same.
It's not trivial to prove it?
In first order logic, no, it's not difficult, but it's not trivial.
Okay, so you're saying what's easy is that there exists an f in some sense.
Yeah.
What's hard is that there is an f that's definable within the system.
I see, okay.
Yeah.
Got it. But existence is not.
Ah.
Existence is not.
No, existence is not. We just did it.
Sure,
Yeah,
sure.
that's right. Yeah.
In fact, there existing an f that's definable in the system isn't always true. It's only true in universal
Okay, so again, what we want is that for our proof system, so our proof system will have a property that whenever it's proving a tautology of this type, we can get from the proof, or there will be a small circuit that computes the interpolant. And then if we have lower bounds on the interpolant, then we have lower bounds on the length of the proof. Okay? And in the resolution, it turns out that, and this is of Krajicek and Razborov, is that the one theorem, and we'll strengthen it in a second, but I just want to explain it. So resolution has feasible interpolation. In fact, if the size of alpha of x, y, and beta of x, z is s, maybe, then the size of f, alpha and beta, is the same, it's roughly, let me write like this. More than this. What?
Is feasible the same as efficient?
Yeah, feasible is the same as efficient. And here I wrote to you exactly what it means. The circuit will be of the same size as the proof, exactly. It will, in fact, look like the proof. So let me tell you why, where it's coming from. And I will not do as many details as I wanted, but you'll see the idea. Okay, but it's really, I want to stress how clever it is to have a proof lower bound follow from a circuit lower bound. First of all, it opens the possibility of conditional proof system lower bounds. We don't, we still have to prove a lower bound on circuits. It's not like we have too many of these, right? I mean, we don't. But this interpolant typically will be some natural function, let's say an NP problem. So if we know that that NP has no small circuits, then we have a lower bound on resolution proofs. Now, you may not be impressed because we saw resolution proofs that don't need to follow from any assumptions. But maybe it's other tautologies that we don't know how to prove. In fact, this one we don't have different proofs for, these cliques versus coloring. We don't have different. The width method doesn't work, and it's not clear. Well, maybe you can. But anyway, there are tautologies which you cannot prove otherwise. And you can think about other proof systems. And for other proof systems, it's much harder to prove lower bound. And sometimes the only size lower bounds we have are through feasible interpolation. The most, let me not write it, the most famous case is the cutting planes proof system. Okay, so I explained cutting planes, working with linear inequalities over the reals. It was, a lot of frustration to try and prove size lower bounds there. And eventually, Pudlak did it. And Pudlak used sort of the known, but anyway. Cutting planes has feasible interpolation where you have to say what the circuits, so I just said circuits, but which kind of circuits? So he invented these special kinds of circuits which can interpolate cutting plane proofs. And then he showed that you can prove lower bounds in this model. And I'll say a little bit more about this in a second. Okay, so you want, of course, you want the size in whatever class of circuit C. Of course, you want this class to be as simple as possible so that you can prove lower bounds in this class. Okay, but let's just think about Boolean circuits first. So what's the idea here? Why does resolution have a feasible interpolation? Because it's such a simple system. So let me just do an example. Suppose we have the following clauses. I'll already write the resolution proof for them. So suppose we have x or y, x bar or z. We resolve on x to get Let me write the clauses on the edges. Resolve on x, then we get, I guess, y or z, right? Catch me if, let's say we have also y bar as a, so we can resolve on y here and get z. And we can maybe have z bar also as an axiom. It's a really easy. We resolve on z and we get the empty clause. Okay? Everybody's happy with this little resolution proof. So it's a resolution proof that proves the same, right? It proves that x or y, this is alpha. X or y bar, and x bar or z bar. Right, so this alpha and this beta, and that's the proof that, yeah? That's a resolution proof of this simple contradiction.
What is x or y, comma, y bar?
These are these two axioms, and these are the axioms. Yeah, alpha is a collection of these axioms. It's a conjunction here, but I write, yeah. Right, okay. Now, suppose I gave you an assignment for the x's. Any assignment for the x's breaks this into formulas on disjoint variables, and therefore one of them must be a contradiction. So all we want to know is which one is a contradiction. Maybe both are, but at least one that's a contradiction. And we want to do it by following the proof. So let's assume that, I mean, in this case, there's just one x variable. So let's say x was 0. Let me do it. Yeah. Here. So if x is 0, what happens? So we have, if x is 0, then this becomes y. This becomes 1, right? So here we resolved on x. This stays y. Now we resolve on y bar, on the variable y, and we get already empty here. So this z bar, is not really interesting because we already got a contradiction here. The contradiction follows from the y's, right? In the case x equals 0, contradiction follows from the y's. And on the other hand, if x is 1, it's a sort of the dual thing happens. I guess we get 1 here. We resolve on x. And so this is z in this case, so this is z. Here, the y is doing nothing, right? Because it was a resolution on a y variable. It's doing nothing, we still get z, right? So this again is not interesting, it's not doing anything, and then we branch on z and get the empty clause, right? So basically, it's clear that if you just wanted if we just talked about algorithms, if I gave you the x, you would have an algorithm to see which piece is connected to the contradiction. It's a simple algorithm. Right? So certainly if you have a proof for this, a resolution proof for this, you could figure it out, whether the y's cause the contradiction or the z's. Maybe both, but at least one, you'll find it. So it just immediate that there is a feasible interpolation. Let me tell you a little bit more concretely how this structure becomes a circuit. I mean, it's not just that you have an algorithm. There is a circuit of the same size that computes this function, the interpolant f phi of x. And the way it does, it just replaces each one of these resolution steps by a gate. Let's say that we want to, I'm not sure, I may switch the alpha and the beta, the 0 and the 1 here. But say that you want the result to be 0 if the y caused it and 1 if the z's caused it. Okay? Then what you would do, you have the y clauses and the z clauses. So these will be ones, and I guess, and the and the y clauses will be 0, and you want to know whether the eventual contradiction you reach, the empty clause, is a 0 or 1 from the y's or from. So you want to do it inductively. And then inductively, the way you do it is every y gate you'll make an or, every z gate you'll make an and, because 2 1s and 1 is here it's an or. What do you do with the x? What kind of gate would you put in the x? What? Say?
It selects one of the bottom.
Selector. Yeah, you select. Select the guy, you know. I mean, inductively, you know whether it was a z or a y clause, and you select. So here, so this is a select. Based on x, you know, whatever the left or the right clause. Yeah, whether it was a 1. Put a selector gate, right? One of them was redundant. That's it. So that's a Boolean function, a Boolean circuit. So now, what's the question? The question is: everybody happy with this? It's a very, simple translation of the proof into a Boolean circuit that tells you whether the y's or the z's cause the contradiction for this particular x. Now, that's good. So, do we have a lower bound for f? Okay, so I gave you we discussed this clique versus independent set. We discussed this clique versus independent set. What?
Do you mean versus coloring, or you mean?
Versus coloring. I keep saying independent set. I don't know why. Clique versus coloring, right? Tautology. I didn't write it explicitly. Maybe we should sort of just write quickly. Maybe I'll go 5 minutes over time. So I want to write the alpha and beta parts of the. So you have x will be a graph. X is a graph, and y will encode cliques, let's say, and z will encode colorings. So how do you propositionally say that the graph X has a k-clique? You can arrange the n nodes of the graph here. You can arrange here k room for which kind of color, sort of which a 0 or 1 depending on whether a variable is in the clique or not. So just 0, 1 variables. So yij. So this will be yij. And what do you want? Well, you want that in every row there is at least 1. In every column. Every row is at least 1. So you want k vertices in your clique. So you want that each one will get a 1. So for example, you have y1 plus y1n. So you have this kind of clause for every color. Every color has at least every sort of. We number the clique vertices, and we just say which one each of them is. So that's a particular clause. And you want to make sure that if you picked this guy to be in the clique and this guy to be in the clique, let's say j and k, you want to make sure in colors, let's say, so in numbers 1 and 2, you want to make sure that there is an edge between them, right? So you would write something like y1 j bar or y2 k bar or I guess x jk, right? So you write these clauses to make sure that these vertices are actually connected by the clique. And then for the coloring, you would do something similar. You'll have just k minus 1 up to n, and you have here the zij's, and here you want to make sure that every vertex is colored, so you have z1 1 plus z2 1, sorry, or z2 1, k minus 1 1, things like this, right? You have a color for every vertex, and then you have another condition that if you, again, you color two things are colored by the same thing, then there shouldn't be an edge between them, right? So it will look something like z ij or z ik or x jk bar. Okay. Anyway, that's a propositional encoding of clique versus coloring. So what do we know? We know that if we had a resolution proof for this contradiction, then there is a small circuit that distinguishes between graphs that have a k-clique and graphs that have k-1 colorings. These are two disjoint NP pairs. These are two sets that have short proofs, those with k-cliques and those with k-1 colorings, and no graph can be both, right? So we would have a circuit for this. Well, it's an NP-complete problem, and even for this restriction, you can hope that it's hard. And if we had a lower bound for this relation, then we have a lower bound for resolution proof of this tautology.
So as of today, we only have a conditional lower bound.
Wait. Now, stare a little bit more at this tautology, and notice it has an extra condition, an extra feature. And the feature is that in alpha, all the x variables appear positively. And in the beta, all the x variables appear negatively. And now if you think a bit more, let me not do it, you realize in the circuit we constructed here, the only non-monotone thing was this selector thing. This selector looks like, I don't know, x and L, or L and R are the left and right children, whatever clauses they were, x bar and right. That's how a selector gate looks like. But if you have this property, in fact, even a weaker property, either if only the x guys are positive, or only the x guy, the y bars are positive, or the z bars are negative, you can remove this and nothing happens. So the result here is actually not only does it have efficient, feasible interpolation, but also it is a monotone if either we have this condition, xi positive in alpha or xi bar negative in beta. In this case, you get a monotone circuit. In this case, we have both. You know, the y's have only positive, the z's have only negative. So we have both, so we get a monotone circuit. So do we know a lower bound for for this? It's, again, it's not the clique function. It's just separating cliques from colorings. Of course we know it. It's Rasborov's result. So therefore, Rasborov and the stronger Alon Bopana, I don't know, n to the roughly square root k lower bound for monotone circuits for this, exactly this, right? Somehow lucky it's exactly this, implies that the resolution size of clique versus coloring gives a lower bound. And that's, I think it's absolutely gorgeous. What I mentioned before is that the same method was used for proving cutting plane lower bounds. Cutting plane lower bounds for the exact same tautology by Pudlak. So let me just tell you what happens in his proof. Cutting planes are not resolutions. Linear equations are added. Okay? Again, it has the same monotonicity property. So I mean, it's the same tautology. It has the same monotonicity property. So you can, can monotonize this kind of selector gates, whatever they are. That's not the problem. But the problem is that because we are working with real numbers, the values that occur in this circuit are real values. So it turns out that the kind of circuit you need to prove lower bounds for, again, for monotone circuits, is to compute the same function, whether a graph has a clique or has a k-1 coloring, in a model which has Boolean gates, where the Boolean gates do some, Boolean gates, they have real gates. So the gates look like you have some A and some B, and you have some output. So this is a gate, and G from R arbitrary monotone, now monotone over the reals, monotone function. These are the gates in Pudlak's interpolation for cutting planes. And now you wonder, how powerful is this circuit model? Of course, at the end, I didn't say how you get a Boolean value. At the end, you put a threshold. You say above it, it's yes, below it's yes. So of course, it can compute only monotone functions, and computes all monotone functions. Ends and ors are particular examples of such gates. So good. So we have a model which is a little weird. What's its power? What can it compute? But it turns out that it can compute NP-complete problems. This model, when you add the real instead of Boolean, can do NP-complete problems. So this looks pretty hard, right? Because how would you prove lower bounds? The second piece of news is that Pudlak takes Razborov's proof and just adapts it to this model, almost without change. So it turns out, despite the fact that this model can compute some artificial NP-complete problems, it cannot. It requires exponential size to compute this particular problem. And that's how you get a cutting plane lower bounds for this tautology. Yeah, I think that's enough. Thanks.